This video is sponsored by Squarespace, the all-in-one website building tool. A girl throws a baseball at a blistering speed of 90% the speed of light, but she's in a train that's already moving at 87% the speed of light. So, according to Newton, wouldn't the total speed of baseball just add up and become more than the speed of light, breaking Einstein's rules? This is the question that I asked my physics teacher back in high school, and his explanation was, no, that doesn't happen because speeds don't add up, velocities don't add up, just like how Newton said. Instead, to calculate relative velocity, use this formula. And if you plug in these values in this formula, you'll always find the speed to be less than the speed of light. But you see my problem with that, right? That's just a dumb formula. I mean, I can use it to solve problems, but every time I look at a question like this, my brain keeps saying that, hey, that ball should be traveling faster than light. Why isn't it doing that? And so I thought of gaining some intuition to do that. I thought, like, let's look at the derivation of it. And when I looked at it, oh my God, it just involves so much algebra and manipulation. And I thought, okay, I'm never going to be able to get an intuition for this until now. After making Einstein and Newton talk for months, I think I finally get it. So by the end of this video, we're going to see why Newton's addition is wrong, how Einstein fixed it, and why relative velocities will never exceed c, all intuitively. So if you're ready for this, let's dive in. We start by asking Newton, buddy, why did you even say that the velocity adds up in the first place? Well, Newton says, if we look at the train and if we wait for 1 second, that in that 1 second, that ball would travel 0.9 c forward because that's its speed. But in that 1 second, the train also goes forward by 0.87 c. So look at the total distance that the ball has traveled. It is 0.87 c plus 0.97 c, giving you 1.77 c in 1 second, and therefore that is its speed, faster than light. Einstein says, well, first of all, let's just make c equal to 1. I mean, it's just so annoying to keep saying c over and over again. That's why physicists love units in which the velocity of light is just 1. Simple, right? But more importantly, Newton, you made 3 boo-boos. First, you overlooked length contraction. Moving things shrink in the direction of motion. At 87% light speed, the train would be contracted to half its length. And therefore, you can immediately see the ball does not travel 0.9 when we look at it. It will travel 0.9 divided by 2. So the speed is already less than what Newton expected. Now at this point, we should ask, well, Einstein, remember, this is an intuitive derivation. How did you realize that at 87% light speed, the length contraction factor will be 2? And Einstein says, patience, we'll get there. But we're already beginning to see how Newton's addition is wrong, isn't it? On to your second mistake, Newton, time dilation. Moving clocks tick slower than clocks that are at rest. At 87% light speed, the clocks will tick at half the rate, which means when 1 second is up in our clock, only 0.5 second will be up in her clock. That means the ball wouldn't even reach the entire 0.9, the end of the train. It would be somewhere halfway in between, which means time dilation further slows down the distance that we see by a factor of 2. And so we'll get another 2 in the denominator, and the speed becomes even lower than what you expected. But Einstein, we've already considered both the length contraction and time dilation, and look, the speed of the ball is still more than 1. What gives? And Einstein says this takes us to the third and the final mistake that Newton made. It's something that we've talked about before. It's the one that solves all the paradoxes. It's the ultimate reality, the relativity of simultaneity. Okay, I'm having way too much fun with this. But the point is, if you look inside the train, then the ball reaching the halfway mark is simultaneous with her clock reading 0.5. But things that are simultaneous in one frame need not be simultaneous in a moving frame. In fact, from our frame, we'll find that her clock will first read 0.5. Then the baseball would reach the halfway mark, which means if we consider simultaneity, the ball would be moving even slower than before. But wait a second. At this point, we can ask Einstein, well, Einstein, how did you know that it is this event that happens first and then this would happen? Like, how did you know that? Well, Einstein says his go-to method is to imagine synchronizing a couple of events. For example, let's say we have 2 firecrackers. and we have a light source right in between. Then we send photons outwards, and they will, because the light source was right in between, the photons will go and hit the firecrackers at exactly the same time. And let's say light can ignite the firecrackers. I mean, this is physics, right? So the firecrackers would explode at exactly the same time. But from the moving frame, what would happen? Well, again, light is going to move out from that point at exactly the same speed in both the directions. But this time, the train is also moving forward. Therefore, what do you see? The firecracker over here bursts first. And from this, we can get an intuition for the fact that the events at the back of the train happen before the events in the front of the train. This is our go-to method. And this would be true in general. You don't really need clocks and synchronization technique. That's just a method, but this would be true in general. And so this means if we go back over here, events in the back are happening before the events in the front, and that's why her clock will read 0.5 before the ball even reaches the halfway mark. But Einstein, how do we incorporate this over here? Good question. Again, if we go and look at things from her frame, then from her frame, the ball traveled 0.9 units in 1 second. Again, these two events are simultaneous. But from our frame, they're not simultaneous. Because events at the back happen first, by the time the ball reaches over here, this clock would have already gone past 1 second. In fact, if you do the math, which we will do later on, we will see that this would be about 1.78. So we will see that ball travel 0.9 units in not 1 second, but 1.78 second, which means the relativity of simultaneity slows down that ball further by 1.78. And so that's its contribution. So if you factor that in, boom, you will find that the speed of the baseball is less than the speed of light. But wait, I know what you're thinking. You must be thinking, what if the train was going even faster? Then wouldn't it give a little bit more boost to the baseball and make it go faster than light? Einstein says, challenge accepted. Well, if we make the train's velocity now 0.98, what about the velocity of the ball? Would it now become faster? Well, Einstein reminds us now all these factors will become more extreme. For example, the train will now shrink to 1/5 its length. The time dilation factor would be about 5. You correctly plug those in and you will still see that there is no way to go faster than the speed of light. Okay, wait a second. What if we don't do that? What if instead we keep the speed of the train the same so that the length contraction and time dilation is exactly the same, but if we just threw the baseball slightly faster? Now it's got to break the speed of light, right? Oh, no, because if now you make it go faster, events are more separated apart, and as a result, you will now find that the relativity of simultaneity factor will be higher. So whatever you do, if you increase this number will go up, and again, you will find that the total velocity will still be less than c. This formula is ironclad, folks. There is no way to go around it. And it should not be very surprising because remember, the whole relativity is built on the postulate that the speed of light is a constant, and it's the same in all reference frames. So it's not surprising that nothing can travel, even if you add velocities, you cannot travel faster than the speed of light. The point, however, was to derive an expression for adding velocities that respected Einstein's postulates, and we have found it. We have found it because we can generalize this now, okay? What if we call this velocity u, the speed of the train u, and the velocity of the ball with respect to train v? Then look, what will be our relative velocity? How to add velocities? It'll be u plus v divided by the length contraction factor, the time dilation factor, and the relativity of simultaneity factor. This is how you add velocities correctly, Newton. Okay. all right. But at this point, we could ask Einstein, well, Einstein, so far so good, but this is how far our intuition can get us, right? I mean, if we want to get an exact expression for this, now we just have to do the algebra. And Einstein says, no. Even for finding the exact expression, there is an elegant way to do it, and it can be as intuitive as, say, building a website using Squarespace, the sponsor of this video. Just like with velocity addition or any physics topic for that matter, let's start from scratch. How do we build a website, a landing page? Well, we need a domain. So Let's go to squarespace.com, click on a button which says get domain, buy the domain you want, and boom, just like that, your domain becomes active. And it comes with Whois privacy for free, which is great if you want to protect our privacy, which is something we should try and do. But wait, neither Newton nor I have any decent coding experience. I don't even know what our landing page should look like. Well, Squarespace has incredible templates that we can start with. So we can just click on, say, portfolio, then find the one that looks pretty for us, customize it by clicking buttons. And in a few hours, in our REST frame, of course, the page is live. But there's so much more. There's incredible analytics to tell us about the performance. They also have great support that will unblock us if we get stuck somewhere. So I think Squarespace truly is a one-stop solution for building any kind of website. So if you want to check your website building intuition for free, then go to www.squarespace.com/FloatHeadPhysics. You can also use the promo code FloatHeadPhysics at the checkout to save 10% on your first purchase. The link is also in the description. All right, back to the video. Okay, Einstein, show me the elegant way of looking at these things. Let's start with time dilation. Time dilation factor is gamma, and we've derived this in a previous video. All we needed is a photon clock and a Pythagoras. Over there we saw u squared over v squared over c squared, but here c is 1, remember that. But there is more to it. I mean, if you look at a table of values of them, you will see the same thing as we saw before. At 87% light speed, the time dilation factor is about 2. 98% light speed, the time dilation factor is about 5. And it comes from this formula. But a more elegant way to look at this is if you square them and add them like this, you will always get 1. Now that might seem like an algebraic manipulation of this, but there's something deeper going on over here. It's telling us something about space and time and its connection with the speed of light. And this is something we'll get back to in a future video. But this is one of the ways in which you can look at this factor. And since length contraction factor is just the same, we already have 2 out of the 3. Both these factors, length contraction and time dilation, is just gamma, which leaves us with the last one, the relativity of simultaneity factor. How do you figure this out, Einstein? And let me tell you folks, this is the most elegant way of looking at things. I've saved the last for the best, only for you because you reached till this part of the video, so you deserve it. Okay, so let's go to relativity of simultaneity. And the way to look at it is, if you have 2 clocks or 2 events that are, let's say, 1 unit apart, and they are also moving very close to the speed of light, then we already know that the events over at the back would be ahead by the events ahead of the events in the front. But can you make a wild guess in this particular case? How much will this clock be ahead of compared to this clock? Just make a wild guess. It turns out to be pretty much by 1 unit. This means, for example, if this clock read 0.3, this would read about 1.3. I find it so fascinating because look, you have 2 events that are traveling at 1, spaced apart by 1, are also apart in time by 1. Isn't that elegant? I mean, isn't that telling us about how space and time are conspiring together? Whoa! But we can now use this to build up a general formula. For example, we could ask what happens if their speeds was not 1, but they were going at half the speed of light. Well, then this just happens to be half. What if they were going at 0.3 the speed of light? Well, then this just becomes 0.3. In other words, whatever is the velocity over here, the discrepancy is just that. U. Isn't that amazing? But wait, this is for when the events are 1 unit apart in space. What if the events were 2 units apart in space? Well, the discrepancy would be twice as big. What if the events were half as much apart? Then the discrepancy would be only half as much. So, in other words, what if the events were x units apart? Then the discrepancy would be u times x. And by the way, when I say x distance, I mean the proper length, the length seen from the rest frame, okay? So if we now go inside the train, look, the two events over here are v units apart in space. And therefore, from our reference frame, they will also be uv units apart in time. Therefore, if this clock reads 1, at that same moment from our frame, this clock would read 1 plus uv. And therefore, from our frame, the ball travel distance v in not 1 second, but in 1 plus uv second. And that's why we have to divide it out by 1 plus uv. And you can now see where that 1 plus uv in the original formula comes from. So if you incorporate that, the relativity of simultaneity is just 1 plus uv. And there you have it, folks, in its full glory. The relativistic velocity addition formula derived intuitively. Wasn't that elegant? But I know what you're thinking. You're thinking, well, this is not the formula in our textbooks. And Einstein says, yeah, of course. I mean, if you substitute for the value of gamma and just simplify it a little bit, you will get the familiar formula that you see in your textbooks. This refined version is efficient for problem solving, and that's why we find it in our textbooks. But for a deeper and more intuitive perspective, I find this raw version to be much better. And I think this mirrors life itself. We often seek shortcuts and efficiencies to boost our productivity, but do take a moment every now and then to appreciate the raw, unrefined experiences, for it is these that often offer the most profound insights. Until we meet again.